The internet as we know it grew up around a DARPA initiative in order to provide resiliency in networking. Um, and the addressing used coalesced around Internet Protocol IP, later became known as IPv4. um, addresses seemed to be sufficient. It was 4.3 billion addresses, and just to kind of put that into perspective, I know that population is what it is, but if you take a dollar bill and you stack 1 billion dollar bills on top of each other, it reaches into the troposphere. It's a very large number. Another way of saying it, if you count one of those dollars every second, it takes you 33 years to count 1 billion. So 4.3 billion seemed adequate for the use of networking around the Earth, um, likely forever, at least at the time it did. The adoption of the global network in order to facilitate just a lifestyle, connected lifestyle, was not really anticipated to the degree that it is now, and is turning out that because of mobile devices and a lot of smart devices, these are known as IoT in the industry, smart devices throughout people's homes and that are consuming addresses needing to be connected to the global network. The easiest way of doing that is to just put them on the internet and then have security communication across the public internet. All these things are burning up a lot of addresses, and in fact, the number of IPv4 addresses has been depleted. The 4.3 billion addresses has actually been depleted. Back in the late 90s, there was also a concept thrown out there just for consideration called IPv6. There was an IPv5. It was theoretical, never put into use, but IPv6 did get coalesced into a standard in the late 90s. I think it was 98 or 99, something like that. But there was still a sufficient IP address for address space out there. There really wasn't a need to transition. What's really propelled the increase is a couple of things. For a while during the .com bust, there was a lot of push to switch over to IPv6 because the trajectory was just very high. But then everything kind of flattened back out again, and the thought was, well, we'll just use IPv4 for the long term. We might get around to IPv6, but the urgency decreased. But with cell phones landing in everyone's hands and pockets, if you actually go to whatismyipaddress.com on a cell phone, you'll see two addresses. One is an IPv6 address, and the other is an IPv4 address. So basically, every cell phone on the planet now is running IPv6. Not 100%, but that's a fair statement. And what they do, the carriers like Verizon, AT&T, T-Mobile do is all those IPv6 addresses are then translated to an IPv4 address on the internet, but they do it with what's known as CGNAT, carrier grade NAT, in order to preserve the number of IPv4 addresses versus the number of cell phones. So you could have 10,000, I don't know if these numbers are right, but just hypothetically, you could have about 10,000 cell phones using just one single IPv4 address. And all those cell phones are using IPv6 addresses. So you have, 10,000 to 1 utilization there, something like that. So anyway, IPv6 is in use to an increasing degree. The trajectory that we're going now is that IPv4 and IPv6 will exist simultaneously for the foreseeable future, where there's some portion of communications occurring in IPv6 where there's large devices need to communicate, like in cell phones. That's one example, and who knows what else is going to come by that's going to consume large amounts of address space like that. So IPv6 is available for that type of use case, and then places where it's just a business who has a couple of servers on the internet, or AWS or Azure providing IPv4 addresses to customers. That's likely going to stay IPv4. Regardless, the reason for IPv6 is more addresses. And let's just kind of talk about that. Couple of things. There's some people who like to teach IPv6 for someone who is familiar with IPv4 and try to make it relatable. I don't do that. It's a completely different animal. You basically just have to throw away everything you know about IPv4 and learn the new address. It's a completely different address. It's a lot more like the CNA addresses in ISIS or IPX, SPX addresses. And I'll show why here in just a minute. But the number of addresses, there's a couple of analogies that are put out there. One of them that I like to use is just, it's so many addresses, you can't even express how many addresses it is. Because when you start doing binary math, every time you go up one number, you're doubling. So we had 4.3 billion at 32 bits. And every time you make a click and you add another bit, the number doubles. So we're at 4.3 billion at 32 bits. And you have to keep doubling up to 128 bits before you get a number which equates to IPv6. Now that number, I think there's a mathematical term for that number. It doesn't make sense. It's completely unfathomable how many addresses IPv6 has available to it. It's staggering. I think one way I heard about it is if the Earth volume was filled with BBs, the number of BBs inside the Earth equated to some percentage of the actual addresses that were available in IPv6. And I think it was something like 7 Earths volume full of BBs or something like that. Anyway, the point being is that just because of the sheer math involved, it's near impossible to run out of IPv6 addresses. Now, my personal opinion is the way that IPv6 is currently being implemented is taking a lot of that advantage away. So let's just start off here. In this picture, you see 64, 48, 16. So in 128 bits, it's actually divided in two right here at the 64-bit line. Now, the way they did it is because a MAC address is, let's see, MAC address is 54 bits. Let me, the MAC address is 54. Sorry, 48 bits, of course. Okay, so we got 64 bits. A MAC address is 48 bits. What has become common is to put the MAC address in these 64 bits of the device that is trying to communicate. But you can see there's an additional number of bits that we need to consume. The way that's done commonly is EUI64. Basically, they just shove this FFFE in the middle there. First half of MAC, second half of MAC, and then FFFE. The one trick, just to make it a little complicated, the 7th bit in the first half of the MAC gets flipped in order to indicate that it's a globally unique address. All right, so we commonly put MAC address in EUI64 format in the second half of an IPv6 address. In 64 bits in the front, because there's efficiencies with making routing tables summarized. These prefix are assigned to ISPs, like, Sprint, global telecommunications companies. They get assigned these prefixes. And what that does is on the planet's routers that are actually running the internet, it helps them say, okay, well, all these prefixes are over there in Europe, and all these prefixes are over in Asia, and just these prefixes are in the United States. So I just have to worry about these prefixes being dynamic. All the other ones are just basically summarized off to a different continent. If that boundary wasn't in place with this large address space, it would crush the routers. The routers would have too many addresses that it would have to keep in their tables, and it would be impractical from an electronic standpoint. So first 48 bits are assigned to ISPs. The second set can be assigned to customers, and it commonly is. And this 16 bits is actually what is unique. And that's actually the addresses that people get to use. So, we did have 32, and actually now we're down to 16 bits. There's actually a decrease when you look at it that way. It's just we're burning these 64 bits right here. 64 bits is a ton of information. We're burning these 64s just with an easy button of sticking the MAC address in there and making it fit with an FFFE. Now, in my opinion, that's inefficient, and at least there's the option at some point in the future of removing that and making it all, the 16 bits and the 64 bits all addressable, and maybe doing something with this later on. Who knows? Anyway, that's the structure of the address. And as I said, it's best not to think of this in IPv4 terms. Just go clean and learn in a new address concept. It's divided into these four character sections. I've heard these 4 character sections called a few different things. What I like to call them, of the descriptions I've heard, the one I like is hextet. It's hexadecimal, and there's 4 of them. So it's a hextet. Maybe I'll pull one. Yeah. So there's 8 hextets in an IPv6 address. Each one is 4 hexadecimal characters. Each hexadecimal character is 4 bits. Is that right? Let's see. Blow this up a little bit. Yeah. So they're looking at this. They're calling it a quartet. I like hextet. All right. It's 2 bytes. Each hex is 4 bits. 2 4 bits equals 1 byte. Another 2 4 bits equals another byte. So each hextet or quartet is 2 bytes. Let's leave that concept alone. Okay. In IPv6, there's certain address types. We're familiar with the 127 address in IPv4 for loopback. There is an equivalent in IPv6 of 1. IPv6 addresses can be collapsed using the double colon. So a normal IPv6 address so on and so forth. And when you get to repeating numbers that are empty, you can collapse them with these double colons. So you'll see it written that way for brevity frequently. Then there's something called a global unicast address. This is a visual representation of a global unicast address, and they start with 2000. But again, I'm not a big fan of this because it's further limiting. We need to have a 2 in the front. So there's 10 digits, but we're saying just 2 in the front. So that in and of itself is limiting. And we're taking the last 64 bits away to put in a MAC address that's got a filler in it. So although it is a very large number, we're starting to whittle it down a little bit. Unique local and link local. These are interesting ones. Unique local has to do with an address that's not available on the public internet. It has to do with the concept of RFC 1918 in IPv4. Now, because there's so many IPv6 addresses, the concept of NAT no longer applies. NAT was a way of conserving IPv4 addresses. When you have so many addresses, there's no need to NAT anymore. So everything can just get a unique address. And this unique local address range doesn't get used very much. And it actually begins, it starts FC, but is commonly used FD. And there's a reason for that, but I won't go into it. It's kind of a long conversation. What is used all the time is this link local, FE80. I had a question on a certification test. I don't remember which certification test it was, whether it was Cisco or Linux or whatever, but it asked me what was the bit value of the first byte of a link local address. Now, in order to answer that, first you had to know what a link local address began with, and they always begin FE80. Then you also had to know that it was divided into 2 bytes at this boundary, and that these two characters were each 4 bits, and they comprise the first byte. So the binary value of the first byte of a link local address is 11111110. That's the that that is the answer to that question. I don't I doubt anyone is ever going to see that question, so I'm not breaking any copyright. But the point being is that link local addresses are assigned to every IPv6 device, and they're used to communicate to other devices within their same physical segment. Kind of like the concept of a broadcast domain in IPv4. One of the things IPv6 does is it kills the concept of broadcast. There is no broadcast anymore in IPv6. What's replaced is multicast. And there is a multicast address for all nodes, which is very similar to the concept of broadcast, but because it's using multicast, it's more efficient. No such thing as broadcast storms or anything. I'll skip over these other multicast addresses that are used in IPv6. Okay. In the concept of unicast, so there's unicast and multicast. There's also anycast in IPv6, but the main two bodies of addresses in IPv6 are unicast and multicast. Here's the global unicast. And the global routing prefix, which, as I said before, were given to the major player ISPs on the planet. And then these are the ones that are sent down to customers if you need a specific one. And then the last 64 bits are what are actually bound to devices using EUI64. And because this concept of EUI64 has been adopted widely, it allows devices to assign themselves link local addresses when they start up to negate the whole concept of DHCP. And once they get their EUI64 address and their link local address, they're able to communicate and obtain a router gateway and their prefixes. With that, devices can communicate outside of their subnet. Here's the FD00, but it starts FC00. But let's see if it says here in my notes. Yeah, self-assigned. There it is. If it wasn't self-assigned, it would start FC, but because these are self-assigned, it's FD. Okay. EUI64. Let's take a look at it. Here's the MAC address. In the middle of the MAC address is FFFE, filler, make 4864. X is the MAC address of the interface, and Z is the administration bit. Now here's the magic that helps get rid of DHCP. And really the only reason for DHCP anymore is if you have auditing requirements in order to track devices on your network at a specific time, in which case you would need some means of centrally identifying devices having a certain address at a certain time. There is no way of doing that. Everything is automatically done in the background with the method that's IPv6 is set up to use. So if there's some kind of security requirement within your organization where that is a necessity, then you still need DHCP. Otherwise, it's all automated. There's a neighbor discovery and router advertisements and router solicitations. So let's see. The router solicitation, since the clients don't know how to get where they need to go, they send out this packet called a router solicitation packet. Routers will then respond with router advertisements, and it tells the clients the gateway and the network prefix. It's all stateless. This is meaning that there's nothing tracking it. It's just done with packets on the wire. There's no database recording what's going on here. And then there's something called DAD, which just ensures that there's no duplicate addresses on the network. The entire process of what I'm describing has a method developed around it called Slack, stateless address auto configuration. Oops. I don't think the folks at IT Pro TV will mind that I was borrowing some of their examples. Anyway, so IPv6. And let me just stop and talk about IT Pro TV. They're a IT learning organization that I've used pretty heavily for my self-study, and I do recommend them. They're great people. They have a tremendous breadth of information technology training videos. They also have training labs where you get to log into real hardware and actually feel what it is like to run some of these commands. And they also have practice tests for a select number of certification paths. I think VMware's ESXi, many of the Cisco certifications, many of the Microsoft certifications, many of the CompTIA certifications. In fact, I think they're the sole partner for CompTIA training at the current time. I'm a big fan of IT Pro TV. I spend a lot of my weekends doing nothing but watching TV. One of the what they call edutainers there, Ronnie Wong, my wife is very familiar with. Anyway, and that is the basic concept of IPv6. The important thing to recognize that is a big, long 128-bit hexadecimal address, which is near impossible to try to decipher as compared to IPv4, because the numbers are so large, it's hard for our brains to wrap around it. But when you look at it as basically two chunks of 64, and one chunk is basically a MAC address just with some filler, and the other chunk is basically 48 bits, which are locked into a continent and a given ISP. And really all we're talking about is 16 bits here in order to actually play with anything. It's actually not so bad. When you do look at it in its raw form, it is pretty long and complicated. Let me just pull up. If I can get this on the screen real quick. They're on the wrong screen. Anyway, sometime go to a screen on a Linux box and ping www.apple.com and you'll see an IPv6 address responded. It's kind of fun to see. Or go on your cell phone and go to the website on your cell phone, whatismyipaddress.com. What you'll see is that first it resolves an IPv6 address, and then it resolves an IPv4 address because the carrier has to translate many thousands of IPv6 addresses into a single IPv4 address. Hope that helped. IPv6 can be challenging. And it took me a couple of times going through self-study programs in order for IPv6 to become natural for me. And it's not so bad once you get to that point, but for me, who has been in an IPv4 only world for the majority of my career, it was a pretty steep learning curve. Not so bad anymore. In enterprise networking, it's almost non-existent. Where you do see it, and if it's going to be part of your daily routine, is if you work for a large carrier, not a small carrier. You'd have to be in one of the large carriers or one of the mobile providers, in which case you'll see a lot more IPv6 around.